一下哦，那个你们用那个电脑教室的电脑都已经比较旧了，那两间电脑教室那个电脑大概都7年了。那我们最近在跟那个这1-2个礼拜在跟那个 Intel 跟华硕在讨论，他们到时候可能会半卖半送，他们的所谓的 AI PC， 对，因为 Intel 他们要推他们的那个 OpenVINO， 你们听过什么叫 OpenVINO 吗？你们都没听过什么叫 OpenVINO？OK， 那这就是为什么 Intel 要推这玩意儿了。对，就因为他们大家都听过 CUDA， 对不对？大家都知道 CUDA 什么啊？那个 NVIDIA 他们的那套系统，那套东西。那 OpenVINO 简单讲就是 CUDA 的 Intel 的 CUDA。OK， 那他们想要推这个东西，那理论上他们的电脑到时候捐过来的话，可以在我们的电脑教室里面直接跑模型，对，包括 LLM 都有可能跑得起来，对 ，inference 当然是小的模型啊，小的模型，但是这个还在谈，那个 finalize 以后，那我是希望他们捐的啦，对，因为我们西藏很穷这样子，对，但我会希望说一台压在价钱，如果我们要出钱，一台压在价钱2万块以内啦。可能1万5啊，什么东西？等于说他们出1半多的钱，我们出1半以内的钱之类的。对，那这样子的话，就到时候在那个电脑教室，理论上你们因为是大2嘛，你们在毕业之前大概就可以用得到。对，应该大3，应该如果要做的话，大概是今年暑假。对，所以说你们下学期有可能会用到。对啊，其实我不期待他们那个什么 OpenVINO 啦。那我只是不能跟他们直接这样讲了，我其实是期待他们捐，他们是讲 AI PC， 那我看的是 PC， 你懂我意思吗 ？OK， 就是我不打他们的 AI PC 的主意，因为讲好说，你看大家都用 CUDA， 都用 CUDA， 没有人在用 OpenVINO， 但是他们的 OpenVINO 理论上是可以用啦，就是如果你们要在上面跑一些模型的话，这你们也可以试试看，听说很难用。对，对，我顺便跟你们讲说，其实我们系上也有那个，也有那个 GPU server， 就是 open 给那个系上的那个学生，就是大学生的那个 GPU server， 那个理论上其实已经买了，去年就买了，然后理论上应该这样怎么讲，就应该去年年底就应该 open 给大家了。但是因为一些就是 SNG 那边的人一直觉得说还没有完全开发完哦，所以说他还没有正式的 open 出来。那到时候我会希望他们在今年最晚今年这个学期结束之前一定要 open 出来。那到时候你们只要有系上的账号，就是那个 Polo 的账号，你们就可以登录。当然它有一些限制啊，举个例子来讲，就是你在上面那个几分钟不用，他就把你踢出去，因为就我们没有那么多那个 GPU 的那个可以让大家全部一起用啦，所以我们就是一定要做一些 sharing。那既然做这些 sharing， 那有人不用就久了就踢出去，所以这个也跟大家先讲哦。但是基本上就是我们到时候，这个是我的那个蓝图啦，就是说就是 Intel 跟华硕捐一些 PC， 然后到时候用 GPU， 就我们的 GPU server。对，至于他们的 OpenVINO 好不好用，那你们自己去试试看，好用最好，不好用也没关系。对，好 ，Anyway， 好 ，Back to our class 哦 ，OK， so in the second part of the hashing, okay, we are going to talk about some interesting stuff, okay. We previously in the last set of slide, I mean, we just mentioned like, if it's like a one hash function, it has tons of issues, right? I mean, but how can we have a good hash function, for any hash function, h, you know, we can always find a set of keys that will cause the average access time to go up very fast. Basically, we just intentionally make those keys collide, right? Make those keys collide. I mean, once you have collisions, I mean, regardless like how you resolve it, okay? I mean, we must be able to find some way to make like a bad situation happen, right? So if you have like a fixed hash function, there's such issue. Okay, so basically an adversary, so a bad guy can pick all keys from, you know, to make collisions. Okay, every key, you know, will be mapped to this I locate. I mean the index I. So eventually, like your hash table will be left to only deal with dealing with like collisions. You know, even I have a way to resolve like collision, like probbing, but with one collision, so you prob to the next location. So if you collide again, you prob to the second. I mean, you need to prob again, right? So if you have n collisions, you need to prob n times, right? So the probbing obviously will grow like linearly, you know, in proportional to the number of collisions, right? So this is like I don't know, as long as you have a fixed hash function, this is not possible to resolve. It's impossible. So the idea here, okay, is that we can pick hash function at random, independently of the keys. What do I mean here? It actually means that we can have a set of hash functions. We have a set of hash functions, and we randomly pick hash functions from this set. Okay, so you know. So even if an adversary can see your code, okay, this bad guy cannot find a bad set of keys because like he doesn't know exactly which hash function eventually will be used, right? Because you have a set of functions there. Okay. So this is the basic idea here. Okay. So I mean, this basic idea can help you resolve like an issue inherently from a single hash function. Okay, so we try to deal with. I mean, we try to use a set of hash functions to get the job done. Okay, this idea is called universal hashing. Okay, so let U be a universe of keys, okay, and let H, this H is very important, be a finite collection of hash functions. So this H indicates the set of hash functions that I just mentioned. Okay, you have a bunch of hash functions there, okay, in the set H. Okay, each will map U to this your table, okay, of size m. So index runs from 0 to n minus 1. So we say H is universal, okay, if for all x, y, okay, for any pair of key x and y, okay, where x is different from y, x, y are different, we have we can find like a hash function such that hx equal to hy. This situation, the problem. Sorry, there's something wrong. Oh yeah. This is like the the number of hash functions, that has like these two keys collide. Okay, the number of hash functions in the H that have the key, these two keys collide. Okay, the number of these hash functions, number of such hash functions, will be bounded by the size of H divided by M. Okay, so regardless of how you choose the X and Y, as long as they are different, we guarantee like, for any pair of different keys, okay, then, the number of hash functions that will in this set H, that will cause this, Hx equal to Hy, they will cause this mapping to collide. Okay, the number of hash function to have such property is bounded by the size of H divided by M. Okay, or put it another way, because we are going to pick a hash function at random from this set, capital H, right? So the chance of a collision between X and Y is going to be small or equal to 1 over M, right? Why? Because you pick hash function from this set at random, right? And the size of H is, so you need to divide this thing by the size of H, right? That's the chance for these two keys to collide by the hash function you randomly picked, right? So that's so this is like this universal hash means like the chance of a collision between X, Y is small or equal to 1 over M if we pick H at random from H. Okay? So obviously this is a very good property, right? But this is an ideal case. But can we construct such a universal hashing? Is there such a universal hashing exist? Actually, there are many of them. We are going to introduce one. Because we don't have enough time. So today we are going to introduce one. Okay? And then, we are going to show you that it satisfies universal hashing. Okay? So, first, universality is good. Universality, not university. Okay, sorry. NCU is good too, right? Yeah. Yeah. But anyway, okay, let H be a hash function chosen at random from a universal set H of hash functions. Suppose H is used to hash n arbitrary keys into m slots of a table T. Then for a given key X, we have the expected number of collision with X will be smaller than n divided by m. Okay, because because we have n number keys, right? Each key, the collision is 1 over n, right? So because we have n keys, so the total collision probability, the expected probability is going to be bounded by n divided by m. So this is like if your H is a universal hashing, so we have this property which is nice. And n divided by m, by the way, is the loading factor, right? We already know that. So we first need to prove this. So before we talk about universal hashing, okay, we need to talk about the proof of this theorem. Okay, so let Cx be a random variable, okay, denoting the total number of collisions of keys in T with X and let lowercase cxy, okay, be 1 if hx equal to hy, and 0 otherwise. Okay, so lowercase cxy indicate like it's an indicator. It's an indicator. If hx equal to hy is 1, otherwise it's 0. Okay, we know the expected cxy is 1 over m. Okay, we get this from universal hashing. Okay, I mean, we haven't shown you a universal hashing instance yet, but let's assume there's such universal hashing exists. Okay, as I will actually tell you that there are many of them, but obviously we can only show you one instance, but at a later time. Okay, but anyway, we get this from. Sorry. Where is it? Wait, this one. We get this one from the universal hashing. And the Cx, capital Cx, equal to like a summation, lowercase cxy, where y, is different from x. Okay. So, expected value of capital Cx equal to, we just replace that capital Cx with this one. Okay, we take expectation of both sides. And then, okay, we know we can put the expectation into the summation, because of linearity of expectation. And then from here, we know it's going to be 1 over m, because of the EC expectation of Cxy equal to 1 over m. And then, okay, because we have n number of y, so n number minus 1, because not excluding x. So n minus 1 divided by n. So this is the, just a simple summation. So that's it. So from here, okay, it's it's n minus, because it's n minus 1 divided by n, right? So it will be bounded by n divided by n. Okay, we just show you this is n minus 1 divided by n, right? And so you say, oh, this is not n minus 1 divided by n, but this is obviously larger than that number. This is an inequality, remember? Okay? So after I show you the proof of this theorem, okay, we need to talk about, one such instance of universal hashing. It's a little bit complicated, but so pay attention to what my explanation. I mean, I would also try to use. I will also use Chinese to explain. 我会用中文再解释一遍嘛 Okay, let n be prime. Okay, so we first assume a prime number n. Okay, and decompose key k into r plus 1 digits. 所以我们先假设我们那个 key 有 r 加一个 digit，r 加一个位啦，位那个 ，OK， 然后每一个 digit，OK， 都是在0到 n 减1，每一个 digit 都是0到 n 减1。OK， 你当然你会说，哎，这个跟这不是二进制，不是那个什么，这好像是比较一个什么 P 进制哦，因为它是一个 prime， 对不对？没关系啦，就因为我们这边是在讨论存在，对不对？就是我们就建构一个这样子的东西。OK， 那至于这个好不好用， 这个我们后面再讲。就是说，就像我刚刚前面讲，事实上 universal hashing 存在，而且不只存在，而且它不唯一，不唯一。我这边只是告诉你说，你有一个方法建构这个东西出来。OK， 至于说这好不好用 ，OK， that's a different story. I mean, OK. So anyway, so because like it has like a r plus one digit, right? So we can represent k like this, k0, k1, blah 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 blah, kr, right? Right? 它有 r 加一个 digit 嘛，从 k0 到 kr， 是不是 r 加一？对不对？ With r plus one digit, okay? And each digit, for each digit, it's it's going to be a number between 0 to n minus 1, right? Okay, so far so good, right? And then, okay, we will, because previously we talked about division method, right? Division method. So this is kind of like division method. So we are going to, pick, a set A to be A0, A1, blah, 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 to AR, where each AI is chosen randomly from 0 to n minus 1. Okay, each AI is randomly chosen from 0 to n minus 1. Okay? So, and we will define HAK to be AI times KI mod n. So this is kind of similar to division method, except that you multiply your KI by AI, right? Where AI is a random number from 0 to n minus 1, right? Right? Okay. So, how many such hash function exist? We use this way to define capital H. How many functions exist in this capital H? Because for each digit, we have n different ways to choose AI, right? So each digit, we have n ways, right? We have n ways. And we have r plus one digit, right? So totally, this capital H, okay, we have m to the power of r plus 1. This many hash functions there. Is that right? 对，这个没有什么问题嘛，对不对？这很简单嘛，就是说我们每一个 digit， 每个 digit 有 n 种方法，有 n 个不一样的这个 hash function， 对不对？那你的 combination 嘛，就乘起来，对不对？这个应该很简单。所以 so far so good, right? You guys are with me. 那你要记得哦 ，you have to remember the size of h is n to the power of r plus 1, because we are going to use that obviously. I mean, at a later time to prove that it's universal hashing. So now I claim this capital H is universal. Okay, so then we need to prove that. Okay, suppose X and Y are distinct keys. They are distinct keys. So X is obviously these two keys, I mean, because we will have to represent them into R plus one digit. So X is like X0, X1, blah, 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 to XR. And Y is Y0, Y1, blah, 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 to YR, right? Right? So they are different. Okay? Then they differ in at least one digit. Right? They differ by at least one digit. Okay? you may wonder what is W log, right? It's abbreviation. Okay, if you come from math department, this is nothing new. This is without loss of generality. OK， 就说不失一般性呐、不失一般性。We can assume, OK, that no different digit is position 0. Okay, you could assume it happened at any digit, but let's assume it happened that the digit 0 is different. Okay, but it's it's okay to make this assumption because I mean for the other one you just do a switch, okay, to digit 0. That's it. So for how many HA will these two keys collide? The issue is we need to find the number of keys that will collide these two keys. Okay, these two arbitrary keys, obviously. So we must have HAX equal to HAY. Okay, if that happens, it implies that this one equal to this one, right? For, obviously. Okay, and I mean, they are the same. I mean, mode M, right? Mode M. And then equivalently, okay, you just move the left side to the right. Move the one side to the other. So you just try to write it like that. Equal to, this is like this is 0, mode M. So far so good, right? This is simple algebra, right? Simple algebra. And then, okay, in particular, because we know like A0, X0 and Y0 are different, right? So in particular, we put X0, Y0 separately from the other term. So we have this, right? Right? And then, okay, this implies, okay, we can move this one to the right, right? Again, I mean, this is very easy, right? So far so good, right? And remember, M is a prime, right? M is a prime. So, and we know X0 and Y0 are two different numbers in the range of 0 to N minus 1, right? In the range of 0 to N minus 1, right? So their difference, if you consider, modulo, I mean, it's also between 0 to N minus 1. Now, the issue is like this. This thing in a has an inverse with respect to M, right? With modulo M. It has an inverse. 你知道什么叫乘法的那个反元素吗？就是说，譬如说一个元素，它有反元素，就是你乘上这个元素会变成一嘛，对不对？那你如果说这两个互值 ，again this is from discrete math, okay? So 好吧，我至少快速的，如果这两个互值，就说如果 P 跟 N 互值，代表存在 A 跟 B 会等于1，对不对？辗转相除法记得吧？你知道吗？就写两个，然后这样弄过来，弄，到最后互值这边最后就1嘛。啊，你可以把那个1写回去，变成 a 乘上第一个数字加 b 乘上另外一个数字会等于1，对不对？那 a、b 当然是两个整数啦，当然有可能是负的，有可能正，有可能负，对不对？我这应该不用再秀给大家了吧？应该不用，对不对？好，那我这边呢，我只要对两边取 mod， 对两边取 mod n， 代表 a、p 是不是？对不对？这个是离散数学应该要会的东西啦，但是没有关系，忘光了都没有关系。我现在再讲一遍，可以吧？讲到这边你有没有问题？从互值，我们知道说，譬如说这两个它的公GCD 如果说是某一个数字，那你知道说你可以什么 AP 加 BQ 会等于那个最大公因数，那这边最大公因数是1啦，所以说你这个就 AB 加那个就会等于1，所以这边代表说什么 ？P 就是等于这不 A 就是 P 的负1啦，对不对？对不对？对不对？这个 A 就是 P 的 inverse 嘛，对不对？对不对？所以如果说这两个数字互值，那代表说在 mod 的那个一个数字下面，另外一个数字它有反元这个乘法的反元素。那好，到这边中文结束可以吗？可以吗？可以哦。OK，so look at here, this number x0 minus y0 and n. These two numbers must be coprime, right? 它们一定互值嘛。所以 in other words, there exists an inverse of x0 minus y0. The inverse of this number, okay? So we can, so let n be a prime for any z, okay, such as z is not 0. Okay, there exists a unique z inverse, okay, such as z times z inverse. You know, it's congruent to 1 mod n. So here I give you an example, but here I actually give you a proof. Not this is an example, but I actually give you a proof here. Okay, as long as it is not 0. Okay, so we know like x0 minus y0 is not 0, right? Because they are different, right? We assume, at digit 0 they are different. Okay. So we have this one, and then because x0 is different from y0, so there's an inverse. We have this inverse exist. So we can multiply this inverse on two sides. 我们可以把这个 inverse 乘在两边哦，乘在左边，这边左边就变成 A0， 对不对？左边就变 A0，右边就变这个都会乘上这个的 inverse， 对不对？到这边你会觉得，那我们这看起来很简单啊，那是什么意思 ？Okay, what does that mean? Okay, it means that, okay, if your A1, A2, A3 to AR, if these numbers have been determined, then remember your X and Y are determined already, right? And if your A1, A2 up to AR have been determined, then A0 is a fixed number. It can be computed from the right-hand side, right? So how many choices of A1, A2 up to AR? A1 you have n choices, right? A2 you have n choices. To AR you have n choices, right? So totally, the right-hand side, okay, if you make this A0, okay, this way, it's going to collide. It's going to guarantee there's a collision, right? Okay, So for any choice of A1 blah, blah, blah to AR, exactly one choice of A0 will cause this X and Y to collide. So for these numbers, how many possible choices are there? We have, there are, n choices for each of A1, A2, blah, blah, to AR. So it means like totally we have how many? We have like m to the power of r, right? We have m to the power of r. This many choices that will make make X and Y collide, right? So m to the power of r is exactly the size of h divided by n, right? What is size of h? The size of h, I told you to remember that, right? It's n to the power of r plus 1, right? And n to the power of r plus 1 divided by m is m to the power of r, right? So we have this. So this is exactly, the property of universal hashing, right?这边可以吗？这是一种选择。This is only one possibility for universal hashing. There are other ways, but I will not show you the other ways. I mean, if you want to check out like other possible universal hashing, a textbook show you other, different ways. But at least here, I give you one instance of universal hashing. So this is not just a theoretical thing. It is possible. It is possible. It can be constructed. Okay? Yeah, I think we will stop here today. Okay? So next time we will start from here. Okay? Perfect hashing. Okay?